Question 9. A particle moves in a straight line so that its acceleration, a meters per second at time t seconds, is given by a is 2t minus 8 for values of t between 0 and 5 inclusive, and a is 2 for t greater than 5. So we have variable acceleration for the first 5 seconds and then constant acceleration when t is greater than 5. We're also told at time t is 0, the particle has velocity 12 meters per second, and we want to find for when it is got the variable acceleration an expression for the velocity of the particle at t seconds. So if we consider t being between 0 and 5 inclusive, the acceleration, which we know can be represented as dv dt, is equal to 2t minus 8. dv dt equals 2t minus 8 is a differential equation, and we can solve it by separating variables. So if we rearrange, dv is equal to 2t minus 8 times dt, and then we can integrate each side. So if we integrate the left hand side, we get v. If we integrate the right hand side, we get t squared minus 8t plus c, a constant of integration. So we have v equals t squared minus 8t plus c. But we do know the initial conditions. When t is 0, the velocity is 12. So if we substitute in, v is 12 and t is 0. So if we sub c is 12 back into the equation, we get v equals t squared minus 8t plus 12. So this is the expression for the velocity as t varies. We could consider these results as t varies. We know the acceleration is 2t minus 8 for the first 5 seconds. So when t is 0, a is minus 8. When t is 1, a is minus 6, then minus 4, minus 2, 0 and 2. But then there's constant acceleration 2, 2, 2 as things go on. We know v was t squared minus 8t plus 12. So when t is 0, v is 12. When t is 1, v is 1 minus 8 plus 12, which is 5. When find v when t is 2, we get 4 plus 12 is 16 minus 16, so that's 0. And we can get these other values. When t is 3, 9 and 12 is 21, minus 24, it's minus 3. When t is 4, it's 16, 28 minus 32 is minus 4. When it's 5 squared is 25, plus 12 is 37, minus 40 is minus 3. But then the acceleration is 2 all the time, so it just increases by 2, so it's minus 1, 1 and 3. Notice when the acceleration is 0, the velocity is the minimum velocity, and we could look at that a different way. So if v is t squared minus 8t plus 12, if we complete the square, v is t minus 4 all squared, which gives us t squared minus 8t plus 16, but we need a minus 4 to make it equal to 12. So the minimum value is when t is 4, and the minimum value is v is minus 4, which is what we got, so things link in there. But we'll have to be careful that we are aware that we have variable acceleration and constant acceleration for the next part. Part B, hence determine the velocity of the particle when t is equal to 14. So we know there was variable acceleration for the first 5 seconds. So if we see where it is after 5 seconds and substitute that t is 5 into this, we get v is 25 minus 40 plus 12, which is 37 minus 40, which is a minus 3. It is now going to travel with uniform acceleration of 2. The starting speed is minus 3, and we want to find out what happens when t has got up to 14, but that isn't when t is 14. That is when it has gone from 5 to 14, so it is 9 seconds further on. So the initial speed u is minus 3, the acceleration is 2. This is going to happen for 9 seconds starting from t is 5. So we want to find v, so we need an equation that links this in, and it's when we've got constant acceleration. So we just use v equals u plus at. So v is minus 3 plus 2 times 9, which is 18. Minus 3 plus 18 is 15. We can also check this with a simple calculation from the idea that it starts off with a speed of minus 3, and every second it increases its velocity by 2. It does that for 9 seconds, so that is an increase of velocity over those 9 seconds of 18. Minus 3 plus 18 is 15. So we can just think of what's happening. Every second the speed increases by 2. So it was minus 3, it was minus 1, it was 1, it was 3, and so on until it came to 15. We could have looked at this last part when t was greater than 5 as the acceleration again is dv dt, which is 2, which is a differential equation, so we separate the variable. So dv will equal 2 dt, and we integrate each side. So v is equal to 2t plus c, the constant of integration. But we know this acceleration started when t was 5, and v was equal to minus 3, so we can sub in. So minus 3 is 10 plus c, c is minus 13, so v is 2t minus 13. But we started at 5 and we went to 14, so v is 2 times 14 is 28 minus 13, which gives us the same answer as 15 meters per second.
Just a little Geogebra app to show you what's happening in this question in a graphical sense. So to start with, if we look at the acceleration, this is these ones in the lighter colours. So the acceleration is 2t minus 8, so when t is 0 we have minus 8 as the acceleration, which is there, and then it goes up to 2 as you saw in the question. And once you get to 2, then we have constant acceleration after that of 2 meters per second squared, or meters per second. And we saw what the formulae were for the velocity in the two sections of the travel. This is the t squared minus 8t plus 12, and then when we get there we have a straight line of 2t minus 13, and we can actually see if that line carried on it would hit at minus 13 there. So as the movement progresses, because the acceleration is changing, then the velocity changes differently as we go along. And of course this line represents the gradient of the velocity. So as we move along, the velocity is dropping quite quickly because we've got a a largish negative acceleration. And then when we get to the acceleration being 0, that is of course when the velocity bottoms out and starts to increase again. So that was the minimum referred to in the question. Now when we get to here, then the acceleration stays at 2, so every time we go along 1 second, the acceleration goes up by 2, and notice the scales are not equal, so we're there at 8 and at 3, so then it's going to go to 5 and then 7 and so on until we get to 14, which is where we have our solution for part B, which was that V was 15.